Hi everyone. Thank you for joining today. Today we have the pleasure of having Zhe give us a talk today. So Zhe is a research scientist and manager at Apple. He works on building large-scale vision, language, and multimodal foundation models. So very relevant work. Before Apple, he was also a principal researcher at Microsoft, and he received his PhD from Duke in 2018. Apart from that, he's also been very active in the academic world and like has served as area chairs in top tier conferences and gotten some honorable mention awards at CVPR and WACV in the past. So without further ado, I'll just pass on the mic to Shay. Yeah, thank you for
Yeah, thank you.
coming in. Yeah.
Yeah, thank you for the nice introduction. Yeah, so it's also my pleasure to give the talk here. And also due to some of my personal conflicts, so I cannot join the talk in person. So I can only do the web, so kind of join the Zoom meeting. So I think the topic of today's so presentation is how we can build a multimodal LM, and also from the so from the pre-training side it goes to post-training and agents. How I can go to, okay. Yeah, so I think the multimodal LM, so it's a very hot research topic. So there are so many, so famous model out there, ranging from so closed source models such as the GPT-4o and also o1, and also recent Gemini 2 and also Cloud, and also even the most recent Llama 4, right? And on the other side, we also have so many good and strong open source model, such as Queen 2.5 VL and other some models. So here I want to briefly talk about so an overview of Apple multimodal research. So I think yeah, the reason I want to do this kind of overview is I think it's also a great opportunity for me to tell people so what kind of some multimodal research so that is happening inside Apple. And actually, so I would say it's quite different from the typical impression Apple has. It's we don't publish paper, but actually we publish a lot of paper. And also recently we are also trying to open source a lot of models, try our best. So here I'm going to only talk about so in the multimodal so in this relatively constrained field, what kind of research that we has been doing. So we have been mainly focused on multimodal LM given the popularity of this topic. So we first have the MM1 model family. We have MM1 and also MM1.5. And then we also have some model extensions such as MM-Eagle and the most recent MM Spatial for 3D so image understanding. And for MM-Eagle is more for egocentric so video understanding. So besides that, we also have the ferret some model family, such as ferret and the ferret 2 for fine-grained so image understanding. So how we can let a multimodal LM that is able to understand the image regions. And so especially one very interesting application of using this fine-grained capability is to develop models that can understand the UI. So this leads to our recent work, such as Ferret UI and the Ferret UI 2. We also do video understanding, actually. From the open source part, we have slow fast Lava, and recently we have the 1.5 version. We know the image encoder is one essential part of multimodal LM, and indeed many of the recent work has been focused on the multimodal LM itself. So here we also want to answer questions like how we can train the next generation of image encoder. So in terms of this, actually we also have several work to train a stronger image encoder for future multimodal LM. For example, MoFi in iClear last year, Clock in submission, AIM, and also MV2 in this year's APR. Data is very essential. We also study synthetic data, especially synthetic data for multimodal pre-training, such as our the VCAP, and also the VCAP V2 work. We also do some kinds of benchmarking for better analysis, such as MapBench and the MiaBench for complex so multimodal instruction following. So reasoning is also a very hot topic. So even before the O1 model so become popular, or the DeepSeek R1 model so become popular, we also have some early exploration. For example, the Lava reasoner, how we can do COT reasoning so with the Lava model. Well, so agent is a hot topic. We also want to so extend our horizon to agents. So one of our recent work is generalist embodied agents. We also have a lot of so visual generation. So the first visual generation work that we have done is the magic work that is trying to combine multimodal LM with a diffusion model for image editing. And recently for the UniVG so work, we have trying to train a generalist diffusion model for different kinds of so image generation applications. We also have DITL and the STIL for video generation. So I think so the STIL work is also from the UCLA. So our great intern so Zhongyu. So last year. So as you can see, there are so many work here, and I think we only have so relatively less than 1 hour here. So I will more focus on some selective so selected work that I'm interested to talk about it so for today. So I will first briefly talk about so MM1, and then for the image understanding, I think that's really so interesting topic. I will briefly mention so clock and MV2. For the poster training side, I think UI understanding is really a very so nice topic, and especially given the GUI agents so recently become even more even more popular for the potential of so computer use agent. Lastly, I will talk about our recent work of agents embodied generalist embodied agents. So depending on the time, to see how much detail so that we can go go into. So first, I will give an overview of so MM1, just to give a high-level background of so what kinds of multimodal LM we are building. So I think maybe so many people are already familiar with this topic, so probably I can be quick. So just as a background, I think this is a standard or widely used multimodal so LM architecture so we typically use. It's a decode-only architecture, which is popular nowadays. Basically, you have a LM, and then you have another image encoder. Surely in the literature, you also have different other choices. Either can be encoder-free or use a discrete image tokenizer. But here we are more talking about the popular choices. We basically have an image encoder that is going to translate your input image into some so image embeddings. But then the length of your image embedding could be long, right? So you want to have a connector to compress this information. And then from the LM decoder side, you will just see a sequence of interleaved image and the text embeddings, which will be sent into LM for you to perform either pre-training or perform specific task at hand. So specifically in the MM1 work, so back then we only so explored the model size from 3B goes to 30B and some MOE variants. From the so vision transformer side, I think so from the image encoder side, so vision transformer is really so good choice. So I think so vision transformer we also have so many variants, right? So for example, swing transformer, etc. So here we still believe using the plain simple disk vision transformer is the way to go. So here we also pre-train our so in-house vision transformer. So note that all the components in this paper, they are all pre-trained by our own. So the vision transformer is we train this vision transformer so using the clip objective ranging from the base model size goes to a junk model size. As I just mentioned, there's a connector. So back then, I think it's so C abstractor is a popular choice or a very recent choice. So back then, so 1 year ago. So what we use is a C abstractor. Basically, it's some like so convolutional like operator, so that you can compress your image encoder embedding into a fixed length of image embeddings that will be sent into LLM. And then after sending into LM, then the model will be used. So we will only put loss on the text token, which is the cross entropy loss. And there's no loss on the image side. So surely there are some recent work, for example, there are so actually many work for unified image understanding and the generation, so that you probably can also enforce loss on the image token as well. But for here, since we are just doing multimodal LM, so the loss is only input on the text tokens. So after pre-training, we indeed observe our model can have strong in-context learning capability. So I think nowadays in-context learning is relatively seems like a less popular topic, since we all focus on instruction following, instruction tuning, etc. But I do want to mention, by doing large scale pre-training, the model indeed can do very strong in-context learning capability. And the many capability that is useful after fine-tuning can already be seen after the model is being pre-trained. So for example, the model can already do counting, can already have this knowledge. And then in the second example, so basically you will lay a red circle on top of the original image. And the model can also learn you want to read out the text inside this inside this circle. And for the last one, so for the last example, so it is even more challenging. It also needs to reason about the image a little bit. Is you need to understand the birthday cake is for 1 year old or for 2 year old, and then when you recognize this, and then you will do some simple math. For example, in this case, is 4 + 1 = 5. So I would say a lot of the knowledge that is useful for instruction tuning has already been encoded or be learned during the pre-training. During the pre-training stage. So surely the model can follow instruction after instruction tuning, so there is no surprise. So the way we build MM1, it's so I think in the MM1 paper, so I think the model architecture is nothing new. It's mainly about the comprehensive studies that we have been doing, kind of also showing so what's the kind of the good recipe to train a good model. So the ablation that we do in the paper back then is largely divided into two kinds of high-level ablation. The left one, the figure in the left is about model ablation. So how we can encode the image, what kind of image encoding, image encoder pre-training that we should do, and also what kind of image resolution we should handle. And on the right is more about data ablation, what kind of data we should use to pre-train the model and how we can do that. In a high level, just from the image encoder pre-training side alone, we have tried to select two representative of methods to pre-train the image encoder. One is CLIP, which is very popular. It's a contrastive learning methods. And then another is the AIM model. AIM model is also developed by Apple. But then instead of using a contrastive learning methods to learn the image encoder, the way to train AIM is very simple. You just treat your image as a sequence of image patch, and then you will auto-regressively predict the next image patch, and then you will just train the model so from scratch. So it's a reconstructive loss and it's a generative. So the loss is very simple. And in the AIM paper, they also show the model can have good scaling property. So have good scaling property. So we have done both. So what we observe, these are some more detailed, so which I will skip. So basically, so we will first do the image encoder pre-training. And then based on this pre-trained image encoder, we will further do multimodal LM pre-training. So the high-level results that we show is besides CLIP, AIM, this kind of purely generative pre-trained image encoder can also have a great potential for multimodal LM. And besides that, it's really the image resolution matters the most, so followed by model size. So I think this kind of also intuitive, which is also widely used in other paper, is you can see since the image encoder, since the language encoder can be, so becomes larger and larger, but seems always the image encoder side is relatively small. And here we also observe, indeed, the image resolution has the highest impact rather than the model size, so itself. So in terms of the VR connector, so I think there are so many choices in the literature, ranging from simple linear layer, simple MLP to average pooling, basically no learning parameter at all, or to some Q-former or convolutional mapping so methods. So in a high level, so what we really found is, so still image resolution matters the most, and also how much so budget that you have. So basically the number of visual tokens you can afford to represent the image has the most important. So it's the most important factor. The other aspects, so especially the type of the detailed VR connector seems has little effect after you do large scale pre-training. So here I also want to briefly so mention the pre-training part. So due to I think this is so relatively so more unique. So for the pre-training here, we actually use so three type of data. One is the image captions, which is also widely used to train the clip model. Another is the interleaved image text data, and also text-only data, which is used to train the LM itself. So nowadays, people usually do clip kind of training in a very large scale. So here we also do large scale pre-training using 2 billion image or text data. And so indeed the example show in these slides, they are looking relatively good, right? So you can see the alt text corresponding to the images quite well. But typically this kind of data, they are very noisy. So here this also leads to our ECCV and iClear paper is we are trying to tackling the problem how we can generate a high quality image captions for potential either clip training or the multimodal LM training. So in the MM1 paper, we have been using 300 million model-generated high-quality captions. So the reason is for many alt texts, the alt text can be very noisy. So instead, even after clip filtering, so clip filtering is a widely used technique to do the data filtering, but even after that, the data can still be noisy. So what we found is, so for example, just the image in the top left. So you can see the alt text for this image is just the address of the house rather than the description or how. So it's really not the description of the image, but then rather the home address. Yeah. So here this means we can improve, or we can try to, the high level idea is we can try to improve this kind of data while recaptioning technique. And then that's the whole idea so back then of our ECCV paper. And then in the V2 paper, we're also trying to train a captioner to generate high quality synthetic captions. And this time, we studied the law across 3 types of foundation model, so besides CLIP. So we have studied the effects of different kinds of image captions for training CLIP, for training multimodal LM, and even for training the diffusion model. And the ask or the key question that we want to answer in that paper, so it's so basically, what kind of synthetic captions is needed for each different type of model? So what is the role and the value of synthetic captions and how they can interact with the original text? So it doesn't mean we want to just discard all the original text at all, because sometimes so I think it is more like a balance. Because sometimes the alt text can also be very useful. Uh, on one hand, the alt text can be noisy, but then on the other side, the alt text can also encode rich, how to say, maybe kind of the implicit knowledge or the common sense knowledge, etc., for the model to learn high level high level stuff. So here in this paper, we have a more careful study on what kind of synthetic data is effective for different foundation model. So feel free to have a check of the paper. So when you have time or interested. So we also have the interleaved image text data. And then this is really driven by the fact that, so we think interleaved image text data is important for the future to training the native multimodal model. For example, if you want to train the model from scratch, because even for the LM data we used to train the LM is basically also this kind of very rich text data. But here the difference is we also insert the images back into the original text so that the model can learn both can learn both the LM and also the image encoder. And know that during all this kind of training, we will keep all the image encoder and LM so weights so totally unfrozen. So basically, the model can try to explore everything or try to learn the model weights so freely, just to update the weights from all the data so it can be. There are more insights in the paper, which I will just skip. And here, indeed, by the end, we trained the model from 3B to 30B. And we also train MOE model. And so indeed, MOE is the future, right? So because so many famous models are trained by MOE. So the MOE can scale the number of parameters while keeping the activated number of parameters constant. So the MOE here that we do is something called upcycling. So when I say upcycling, it's basically very simple. It's so because for an MLE model, it's basically in each layer of the MLE layer, instead of you having so for a transformer block, right? Instead of only having one MLP, but then here you will have a set of MLP, and each MLP will corresponding to an expert. So when we do upcycling, this means for all these experts or for all these so MLP, the initialization will be the same. The initialization will just initialized from the original dense model. So this is called the so-called sparse upcycling technique. That is published previously and used in our work. So back then we only have two MOE. One is 3B in model sites, another is 7B in model sites. And so there are two ways that we can do it. So the beginning is you have a dense LM, and by the end is you have a MOE like multimodal so model. Then we can do two ways. First is you can first upcycle your dense LM into an MOE LM, and then you can do multimodal so pre-training. And then the second way is you can first do multimodal pre-training to make dense LM into a dense MM1, and then you can do upcycling. So we found both works, but then so for stability, in the paper we mainly just using the first strategy to train the MOE so multimodal model. So no surprise, we get pretty good results back then, and also the instruction tuned version also so performs nicely back then last year. So we will not go into the detail. But indeed, I want to talk about briefly briefly about some new work that we have been done on the image encoder side. So here the question that we want to ask is what would be the, well, so how we can further enhance the CLIP basically. So the high level idea is, so CLIP is really widely used. And on the right, you can see this is a paper published last year from NYU, right? So probably, so 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 many people have so know this work. It's called the Cambrian one. So it's no surprise. The paper show there are so many image encoder out there before multimodal LLM is popular, but seems by the end, clip-like model is the most powerful one. And here, the most powerful one is the C-clip. But we also consider C-clip is in a high level is roughly uh, so it's also by language so supervised so trained clip model so in a high level. So here we want to ask, so really clip is the best. So can we have a better so image encoder backbone for multimodal LM? So here one specific aspect that we want to improve is to improve the localization capability. So when I say localization capability, it's the image encoder itself can also have very good so image region understanding. So this is different from so many so clip variants such as region clip or other methods that they will crop the image region out and just treat that image region as a complete image. So here we want to so here what we do is different. So basically it's in the sub figure 2. So it's so first you have an image, and then you have an image encoder, right? Just like what the clip looking like. But here we add another prompter. So and this prompter will help you to get the image region. And suppose you also have the region level supervision, which is the pseudo label that we are going to have in the first step. So suppose you have a scalable large scale region text supervision instead of image text supervision. And then you are going to use this image region text supervision to train the model. How can we do that? So this is basically the high level, the question that we are going to ask. So for the data part, I would skip. So it's basically by the end, we can have large scale region text supervision. And also I want to make a connect to the previous work that we have. So in the very beginning, we have the recap work. And then we extend this work to recap V2. And here we have the VESL is basically from that data, we do some further filtering or further processing so that by the end, we will have a large scale region tags, so supervised data, so which will be used for our model training. So the interesting part is on the on how we design the so-called promptable embedding. So here it's we want to get the regional embedding. So there are many ways you can get the regional embedding, right? So if you know the location of the image region, the bounding box location, you can use ROI polar or some kind of this technique to get the image region embedding. So here, so because we want to make the whole work is just a transformer, and also to make the model scalable. So what we do is, so very interesting, is something similar to SAM. So, but then in the SAM model is you have a prompt, but then through this prompt, you are going to get a mask. And then in our clock model, we have a prompt, but then the output of the prompt is a regional embedding. So this is what we do in the high level. It's a, so you will have your original image encoder as you will always have for clip model. So which is, so X is an image. Through an image encoder, you are going to get a set of image embeddings. And here you consider your box, your bounding box, as the prompt, or the so-called visual prompt. And then you will encode this through some positional embedding and one layer transformer so that you will get the information of the box as the prompt. So then you will use this feature to prompt your image encoder to get the regional to get the image region so embedding. So I think this idea is very, yeah, at least I feel very good about this idea. It's very so interesting. It's so basically it's also similar to a text prompting, right? So it's but here you are going to fuse your original image encoder feature plus some conditioner or the prompter or the visual prompter and fuse them together to get the image region so feature so that this is more scalable. So this means given one image, suppose you have so many image regions, instead of calculating the image region embedding for every so image region separately, but now here you only need to encode the complete image so information into a set of embeddings, but then you just add a different bounding box visual prompt so that this feature will be translated into image embedding feature. And then the rest is relatively more straightforward. After you get the region feature, suppose you also have the data engine to generate the region text supervision, then you can just do clip-like training. But now this time you are not in the image text level, but then in the region text level. So that's basically the very high level idea that we do in the clock paper. And this is maybe more detail. It's so besides the original clip loss, which is to enforce, you also learn the original clip information. We also added the clock loss, which is the description I just had, the region text supervision. So by the end, to stable the training, we also added another grounding loss. And in this grounding loss is basically so in the clock loss, you can consider this is like referring from bounding box to region caption. And for the grounding losses, we do the opposite. We also add a box regression loss. So by the end, you will train the model by combining the three loss so together. Well, so for details, really, so feel free to check in the paper. So if you are interested, but here is more like a high level picture of what we do. And after the model is pre-trained, you can just replace your original clip model you have been using. But here, besides the original image encoder, you can also plug in the learned prompter into your multimodal LM so that the model can natively understand your image regions by design. So very quickly, I will talk about AIM to AIM v2. So the high level is in order to further upgrade AIM to AIM v2, we want to also leverage language supervision. But then this time, do not do contrastive, but then let's do the generative part. So in AIM v2, so I would say all this work, they are connected. So in AIM v2, you can consider this is very similar to MM1. But then this time, instead of training the multimodal LM itself for multimodal understanding, now let's just randomly initialize the image encoder. And then the target is to pre-train the image encoder itself. Then everything is so making sense. And then you put some additional loss on the pixel side. And if you are familiar with the literature, this also make a good connection to the kappa work. So which is also by Google, it's using an image captioning loss to pre-train the image encoder. So for details, feel free to check in the paper. But then so here we can see the MV2, this kind of pre-trained image encoder is also scalable. I mean, they have a good scaling property. Well, but indeed, I cannot answer which encoder is better. So I think this is all open research question. And I think this is also the beauty of research, right? It's so you have different choices and then you can do different kinds of training. And let's see, so which one will be the, yeah, so be the future choice. So then, yeah, due to time, I probably need to transfer into the post-training part. So for the post-training part, I think it's basically how you can enable your pre-trained model or for many model, like Lava kind of model family, there's no pre-training at all, right? They so basically directly do post-training. So this can enable high resolution text-rich, so text-rich image understanding, and also fine-grained image understanding bounding box, so etc. So here another two interesting cases: UI understanding and also surely video understanding. So in MM1 paper, we do a very careful study, and especially I think one shining point of MM1.5, I want to say it's so in that paper we can support a very high resolution so image so processing. So by the end, our MM1 model can support up to four megapixel so image understanding, so which can go beyond the current benchmark setting. So it's yeah. So this is just some careful study. I think we can skip. Maybe we can. So if you are so if you are interested, feel free to jump into the paper. But here, in order to motivate further UI, so which I'm going to talk about, I want to first briefly talk about Ferret itself, so that I think it's easier for me to motivate further UI, which I think is so very interesting, because this kind of fine-grained understanding is very essential for UI. So in order to motivate Ferret UI, let's first talk about Ferret. So high level is we want to make multimodal LM have another one capability. It's fine-grained image understanding. First is referring. It's not only in the whole image understanding. If I just point to one region, and then the pointing methods can be flexible, right? So it can be a point, can be a box, or can be any free-form shape so region. So can the model can still understand this specific very small region? So this is the question that we want to ask. Or no, so we try to answer. So another is grounding. So basically, when the model is asked to provide more detailed information to localize the objects, we want to let the LLM can do this job so natively. So when I say natively, it means it's not dependent on an object detector or grounding model outside, but then the multimodal LLM itself can do this job. So what do we do? Then combining the referring and grounding together, then this is our Ferret model. So it's basically we can support any freeform shape input referring. So which is can you so you can also call the visual prompting, right? So really depends on the terminology you want to use, and also using the bounding box as the output. So for example, here the second example is how to make the food region 0 with the current so ingredients that you can see in the image. And then on the right, the model can give a detailed answer. But then not only text response, but then also provided all the so referring to the detailed image region. And then in the first UI2, no. So in the first two, so what we do is basically borrowing the most recent technique. So basically, it's you enable AnyRes so that you can deal with high resolution image encoder and some other technique. But then I would say supporting AnyRes is the most important thing for the image to look more detailedly or can see in more detail. So basically, by the end, this is the kind of model that we can deal with. It's so given one image, even for a small region or very tiny region, our model can also understand so what's inside that tiny region. So yeah, so the basic idea is to support a high image encoding for the referring and the grounding task so as well. Well, with this motivation, we can talk about briefly about the further UI so work. So fine-grained image understanding for natural images, I think is good, right? Indeed, there can also be many applications. So you can understand your natural image in detail, which location goes to where, and so where is this object and that. But really, what's the very unique part of fine-grained so image understanding? So I think it's the so I think this is the UI understanding. So UI understanding is very so the capability of a fine-grained so understanding is very essential for UI understanding. So here, when I say UI understanding, so it's basically now your input is not an so natural image, but then your input is just your iPhone screen, for example. And the inferred UI will mainly focus on iPhone, but then in later work we also extend its application to other device type. So your input is your so in this case, your input is your so your iPhone screen, and you want to have a very detailed understanding of this iPhone screen. Why this is important? Consider later on you want to build an agent, right? This kind of refer and grounding or fine-grained understanding is very essential for UI agent. It's so for UI agent is basically in every step, you want to know where I should tap and what's the action so I should do. So you want to have very fine-grained understanding of your UI. And this is the purpose of Furried UI. So back then we have designed many different kinds of elementary tasks and advanced tasks, and then let the model to learn. So on the right, there's a more detailed example of so what kind of capability the further UI so model can know. So basically, I think the model have a very good understanding of the iPhone screen. So you can ask many questions about your iPhone. Yeah, so maybe so I don't need to go through the example in detail, but feel free to check the paper. So I think favorite UI from the model architecture wise, so it's really there's not much novelty. So it's really about the data and its application to this so UI domain. The other parts I think is standard. So it's like a standard multimodal LM or a modern multimodal LM. So like so every other paper is using, but then the unique part is on the data. So back then we have a more detailed analysis on how the results are looking like and how we also designed so benchmarks that can evaluate the performance or the capability of a model to understand the iPhone screen or the UI. So these are some more, so I kind of thinking I'm so putting too much content into the talk. So probably I still need maybe 10 minutes so before we can do QA. Well, but yeah, so let's see how it works. So basically there are some so visual example, you can have a good understanding of the iPhone screen. You can so let the model so the only difference is in this UI model, right? It's a free-form response. But then if you make your free-form response into more structured response, then this become an so agent model. Yeah. And then in the further UI2, this is our iClear paper. We extend the understanding. So now it's basically we want to have one model, but then this one model can not only understand your iPhone, but can also understand your iPad and also understand your web screen, which can be often used in Mac, and also even understand your Apple TV if you use it. So the key is still data, but then so besides data, I think there's not much novelty so there. So as long as you have the data in this kind of format and this kind of so platform, then you can train such a model to do such kind of job. This is more detailed design, and also by the end, we can have one single generalist UI understanding model can have a good understanding across different platforms, which can be useful for navigation and agents. Well, maybe I need to another 5 minutes probably. So maybe let me so briefly discuss this work. It's well, then we can also surely have more detailed discussion during our one-on-one. It's so multimodal LM itself cannot take action, right? So this is so what we all know because your output is a text sequence. So here is basically transform your vision language model into a vision language action model. So then this is so what we want to do is so generalist so agent. So we want to have one single agent that is can do robotic manipulation, navigation, games, and UI control. And then the difference is now instead of using static data, now you have interactive data. But then how we can do that? We can surely go beyond SFT, right? Go beyond the supervised fine tuning. So if I want to summarize if I want to summarize this work into one sentence, the sentence will be do online IL. So it's very important and very unique for the generalist agent. So IL is super important. And now how we can transfer a base LM, base multimodal LM into the embodied agents. So we do IL, but then surely IL is not enough. We also need to do SFT so that the model can have so that we need to first have a strong base model on this embodied task. And then we do IL, which is super important. So by the end, the results is we have one model that can do many different tasks and then generalize to new settings. Then how can we do that? Well, architecture-wise, it's simple. It's mainly about the implementation, how you can make it work. So you have your language instruction as usual, and then you have your input observation. Now the observation is not a text-rich image or a natural image is not, but here it's so it's your visual observation. And actually you have many visual observation. You also have your history of visual observation. And then you have an output. You also do autoregressive so prediction. But this time, so it's not a text prediction, but then you want to take action, right? So your output is the action space. But then LM can only output the text, right? But then for agents, we need to require action. So how we can do that? So basically in the paper, we have two kinds of action. One is the learned tokenization for the continuous control task. Another is the semantic tokenizer, which is basically original LM vocabulary. Then so by the end it's a multimodal LM, but now you can take action. So you transfer your vision language model into a vision language action model. Then we do two steps of training. So in the first stage, we only do SFT, but then in the second stage, we also do online IL to boost the performance. Well, let me be quick. So in the first stage, in the SFT part, so I think you have all kinds of so this kind of interaction data. But then one unique part is you also need to use your original VL data. So this is corresponding to the data you are going to use for your multimodal LM fine tuning. Skip. Then you are going to do IL. So because you will see SFT is not enough. Yeah, skip is how you want to do IL. It's using PPO, etc. Yeah, probably also skip. Yeah. Yeah. So I think yeah, maybe this is important. It's so by the end we think online IL is very important, and also the base model itself is only so it's also important. So in this figure, the green one that we have here is a multimodal LM performed with online IL, but then it's not using. So basically, this is the original multimodal LM, but then directly using online IL, you can see it can improve the performance, but it may not be improved that much. And then on the right side is we first do SFT to let the model understand our current the task you are going to deal with, and then do online IL. You can see the performance can so the first SFT stage is very important to accelerate IL training. Yeah, this is maybe too detailed discussion. But here I also want to say, so the model is not perfect. So by the end, I think this is only the beginning. So I think here is relatively something that we call generalist embodied agents. But on the other side, we also feel by the end, since this model may overfit a little bit to the current task that we have, and we also want to work further to how to push the boundary of this and how to make the model or the agent really generalist. So this is also, yeah, some more work that we need to do. So the high-level takeaway on this part is doing IL. Yeah, so IL is very important to train the agent. So if I want to just say one sentence. So by the end, I think a summary is I think we have so many work that is happening inside so Apple on the multimodal research side. And then some future direction, I think surely clearly so unified multimodal understanding and generation is a hot topic. And really, what kind of role vision can play in multimodal LM? Many in the case, people just using CGLib, and then that's all. And the reasoning and also agent, I think how we can push IL further. And also synthetic data is important for agent. Yeah. And especially, yeah. So I think those are all quite interesting topics. Yeah. Well, I probably talked too much. Yeah. Then that's all for today. Yeah. Cool.
Awesome. Let's thank our speaker once. Um, we'll take questions now. So if anybody who has any questions, just please unmute yourself and ask the question. I'll take a look at the chat as well if anybody asks any question. Yeah.
I have some question. Actually, quite some question, but I also have have a thesis defense to go in 4 minutes. I'm mostly interested in the grounded work that the ferret that you mentioned, and I think you said the most important thing is the data. But I wonder, maybe you mentioned I didn't hear the detail. How do you get the data? Do you collect human annotation or you use another model to get this bounding box data? I think that's one. And another is reasoning. So you only mention it in your future work. But I don't believe you've mentioned any reasoning effort that you're currently doing. I wonder whether like what's going on there, maybe just high level, whether you guys are focusing on data or a model or what for reasoning, for multimodal reasoning.
Yeah, I think that's a all very good question, I would say. Yeah, so I think for the understanding part, I think especially regarding the UI understanding, right? So we have some internal data, but then I think from the open source community nowadays, so getting this data, there are also many public data. So now, so I think for example, UI Taras and also the show UI, right, and also the uground. So there are so many paper now. So back then, I think our work is relatively, well, I would say pioneering, but then nowadays we have also many good open source data that we can use. And in terms of the internal data we have is indeed, so we have some so internal so detection tool that can generate such bounding boxes. And then these bounding boxes and the corresponding metadata will be used to train such model. But then nowadays we also have from the open source community, we have the omniparser, right? And also some other tools that we can use to generate the data. Yeah. And so I think the unique part of this data is indeed the Apple related data can be unique is due to there's no way for other people to simulate such data. But then for other data type, so usually there could be open source environments that we can so generate the data. Yeah. So I think that's also why the Android is easier to get the data is due to the whole system is open sourced. Yeah. In terms of the reasoning, indeed, we don't have time to talk about. So I think there are many interesting work happening. So I think in the high level is I think DeepSeek R1 kind of so like idea, and also IL, and also well I would say multimodal reasoning. There are so many work recently, right? And all with a similar name, right? R1 vision R1 one vision multimodal R1 all the name they just iterate all the different name. So So inside Apple, we want to do some relatively longer term work inside. So for example, how we can do scalable IO. Yeah, this kind of, yeah, but I cannot talk too much. Yeah, but there are many work happening also. So around the reasoning. Yeah.
I see. Right. I mean, I'm particularly interested in multimodal reasoning because I think it's actually lagged much behind the text only. And the effort that you mentioned, at least the ones that I'm aware, mostly they try to distill data from stronger model, mostly still on the text side. And I think the issue that what's unsatisfied is that the reasoning is not grounded. That's why my two question is it's connected. Like you have the grounding and then there is this reasoning. I think from my perspective, like for multimodal reasoning, perception is a bottleneck, grounding is another bottleneck. Of course, you can generate the reasoning path or chain of thought based on text only, which means this is a reasonable chain of thought text. But the issue is how do you make sure then it's grounded to the multimodal context, thus you can use that to solve your problem because it's relevant. Say this is a mathematical problem, or you have a picture of a triangle, right? Then if you don't, you have a reasonable reasoning path, every step is correct. But if you cannot ground your reasoning back into your figure, then how would you solve the problem? I think that's, yeah, I don't know whether you guys have been doing anything specific, but
Yeah, we haven't actually. Yeah, so I think you answered the question by yourself. So for the multimodal reasoning part, I'm also the beginner. Yeah, I just feel the current work is more straightforward, but then really I also don't know how to. So I think as you said, the current multimodal reasoning is more like heavily rely on the LM part, right? And just add a small
right.
image encoder into it and then make it multimodal reasoning. Yeah. I don't have a clear answer yet. Yeah, but that's
Yeah. Thank you.
well, so I think we also have a proposal on this. Hopefully we can start collaborating on this. Yeah.
Okay, thanks.
Cool.
We would probably, yeah, we can take one last question if anybody has any, and then we would probably move on to the one-on-ones.
Just add one question. Yeah. Yeah. So hi Jay, thanks for your help. Actually, I'm an intern at Apple last summer and this summer, so I think I've actually seen you around. But yeah, my question is actually related to Ferret UI. I was wondering, basically you mentioned how different kinds of like products, like for example, this is an example on the iPhone, right? But just wondering how you would kind of adapt this to like Apple Watch or maybe in Vision Pro. I know you just get different like input image sizes, but other than that, what are some other ways maybe to like modify this, or what do you do differently? Yeah.
So I think there are two answers. The first one is hopefully the model can have a relatively good, strong generalization capability. So you don't need to collect the data on every device you are going to add. Maybe out of the box, the model can already understand the UI that so that you want the model to understand. And the second one is surely if this is not enough, you need to get the data. I think this is really the challenging part. I think this is also, well, you just mentioned iWatch, right? But then this is also one of the reasons why we don't have iWatch here. It's getting this data is challenging. It's also happen to be we have the iPad data, we have the Apple TV data, so we can do this. So I think architecture-wise, all these models, they are similar. It's just about the data. So if we can get iWatch this kind of data through either synthetic way or human annotation, yeah, then this can be solved. Yeah. So relatively, I think grounding is a relatively easy task compared with planning. Yeah. Compared with like doing a GUI agent. Yeah.
Got it. Yeah. Thank you.
But then the problem is you need to get the data. Maybe
Right.
not
Yeah.
Awesome. So yeah, I think we are running a bit of time now, so we'll end the meeting and let's thank the speaker again. Thank you, Jay, for the wonderful talk. We will continue to have the one-on-ones on this same Zoom link so that you don't have to switch between Zooms. So you can stay here, and I think whoever is in their one-on-one slot, you can just come at the desired time and join the Zoom link. And yeah, please let me know if we run into any issues. But yeah, that's how we'll try to proceed for the second half of the talk. Yeah.
Yeah, thank you. Yeah, I probably need to take 5 minutes.
Sure. Please do. Yeah.
Oh,
You can rejoin on the Zoom link. I think it will be open, and yeah, should be fine.
sounds good. Yeah, thank you.
Yeah.
Hmm?
Hey Brian, are you here for the first meeting?
Yeah, maybe we can stop recording.
Oh yes, we should. Yeah, thank you so